Ever wondered how our universe was created and how it became the seemingly infinite space we know today? This mystery has intrigued and puzzled philosophers, scholars, and scientists for centuries. Imagine a vast expanse of nothingness suddenly erupting into a cosmic dance of particles and energy, giving birth to the universe as we know it. This isn't just a figment of imagination, but a widely accepted scientific explanation known as the Big Bang theory. According to this theory, our universe was born from a tiny, densely packed singularity around 13.8 billion years ago. In an instant, this singularity started expanding, and thus, our universe began its journey. This theory, backed by numerous scientific evidences, has become the consensus among scientists, astronomers, and cosmologists around the world. It continues to shape our understanding of the cosmos and our place within it. So are you ready to dive into the fascinating journey of our universe's creation? The Big Bang theory sounds complex, doesn't it? But the essentials are quite straightforward. It's a tale of creation, not of life, but of the universe itself. Picture, if you will, an incredibly dense, hot ball of energy. This is what scientists call a singularity. The singularity was not large, in fact it was infinitely small, yet it contained all the matter that makes up our vast universe. Around 13.8 billion years ago, something extraordinary happened. This singularity began to grow, to expand. It wasn't an explosion, so to speak, but an incredibly rapid stretching of space. This is the Big Bang, the moment that our universe began to exist. Now you might be wondering, how did everything we know come from this tiny, hot, dense point? Well, as the singularity expanded, it cooled down. The energy it contained started to change, to transform into particles. These particles were very basic, things like quarks and electrons, the building blocks of the atoms that make up everything we see around us today. Over time, these particles began to combine. They formed atoms, the atoms formed stars and galaxies, and over billions of years, these stars and galaxies formed the universe we know today. But it's not just about matter. The Big Bang also gave birth to the laws of physics as we know them. You see, in the extreme conditions of the Big Bang, the laws of physics as we understand them today didn't apply. As the universe expanded and cooled, these laws began to take the form we recognize now. So, to sum it all up, the Big Bang theory tells us that our universe started as an infinitely small, hot, dense point, a singularity. This singularity expanded, cooled down, and eventually formed all the matter and the laws of physics in our universe. A tiny, dense ball of energy exploded and expanded to create the universe we live in. Fascinating, right? Let's put this creation into a timeline, shall we? Picture it. Around 13.8 billion years ago, we're at the start of the universe's timeline in a period known as the singularity or Planck epoch. This is the earliest known period of the universe, where all matter was squashed into a single point of infinite density and extreme heat. It's hard to imagine, isn't it? The quantum effects of gravity were the dominant physical interactions during this epoch, with no other forces coming close to their strength. This intense state could only last so long, and so the universe began to expand and cool. This led to the manifestation of the fundamental forces of physics as we know them today. All this action, from the first moment to the expansion, happened in a blink of an eye, cosmically speaking. From a single point of infinite density, we've come a long way, haven't we? After the singularity came an important phase called the inflation epoch. This epoch was a period of rapid exponential expansion in the early universe, kicking off around 10 to the negative 32 seconds after the Big Bang. During this time, the universe's size grew at a mind-boggling rate, driven by the immense energy of a field of physics we call the inflation field. The universe at this juncture was filled with a high energy density, and the enormous pressure and temperatures resulted in this swift expansion and cooling. This inflation helped to smooth out the universe, ensuring that matter and energy were distributed evenly across space. The inflation epoch was not just a period of physical expansion, but a time of transformation. The energy of the inflation field was converted into matter and radiation, setting the stage for the formation of atoms, stars, and galaxies. And so the universe continued to expand and evolve, leading to the cosmos we witness today. We've journeyed through the creation of the universe together. Now let's summarize what we've learned. The Big Bang theory suggests our universe originated from a singularity, an incredibly dense and hot point, about 13.8 billion years ago. The universe then underwent a rapid expansion known as the inflation epoch, leading to the manifestation of the fundamental forces of physics. The understanding of our universe's creation is indeed a testament to human curiosity and our relentless quest for knowledge. Until next time, keep exploring, fellow science enthusiasts. Following the inflation epoch, our universe entered a new phase, aptly named the cooling epoch. As the universe continued to expand, it also progressively cooled down, leading to some very significant changes. For one, the universe's temperature dropped enough for the first atoms to form. Prior to this epoch, the universe was a hot, dense soup of particles, too energetic for atoms to exist. But as the universe cooled, protons and electrons began to combine to form hydrogen atoms. This pivotal event led to the release of the cosmic microwave background radiation. The radiation that we detect today as a faint glow in the microwave range is the relic of this critical moment in our universe's history. Most importantly, the universe became transparent for the first time during the cooling epoch. Before this, photons of light kept bouncing off free electrons, unable to travel any significant distance. But once these electrons were captured into atoms, light was finally able to travel freely. The cooling epoch set the stage for the formation of the first stars and galaxies, marking the beginning of a new chapter in the history of our universe. So stay tuned as we continue unraveling the mysteries of the cosmos. Following the cooling epoch, the universe transitioned into a profound phase known as the structural epoch. This epoch heralded a significant transformation in the universe as we know it. As the first atoms formed during the cooling phase, they began to gravitate towards each other, eventually igniting to form the very first stars. These stars, in turn, grouped together to form the inaugural galaxies, setting the universe alight with their brilliance. But it wasn't just the luminous matter that played a crucial role during this epoch. Dark matter, an elusive and still not fully understood substance, had a significant part in shaping the universe's structure. It acted as a cosmic scaffolding, its gravitational pull influencing the distribution of galaxies, leading to the vast cosmic web we observe today. The universe evolved from a relatively smooth distribution of matter to a clumpy, structured one. With galaxies clustering together in a complex network of filaments and voids, this transition was driven by gravity, as areas of higher density attracted more matter, leading to the formation of galaxy clusters and superclusters. The structural epoch marked the birth of the universe as we know it today, a universe teeming with billions of galaxies, each housing billions of stars. This epoch laid the groundwork for the complex cosmic structures and the intricate patterns of matter distribution that we observe in our current universe. Stay tuned as we delve deeper into the cosmos, exploring the mysteries of dark matter and the evolution of galaxies in our next segment. Having traced the universe's journey from the Big Bang to the formation of complex structures, we now turn our gaze to the future. So, what does the future hold for our universe? The universe, as we understand it, continues to expand at an accelerating rate. This expansion is driven by a mysterious force known as dark energy, which counteracts the gravitational pull of matter and causes galaxies to move away from each other. Several theories propose different outcomes for the universe's ultimate fate. The Big Freeze theory suggests that as the universe expands, it will eventually become too spread out and cold for life as we know it to exist. The Big Crunch, on the other hand, posits that the universe's expansion might reverse, causing everything to collapse into a singular point. Then there's the Big Rip theory, which proposes that the universe's expansion could become so powerful that it tears apart galaxies, stars, and even atoms. The role of dark energy is crucial in these predictions. Its exact nature and influence are still subjects of ongoing research, holding the key to understanding the universe's future. While the future of the universe is uncertain, one thing is clear: our journey of discovery is far from over. Join us as we continue to explore these cosmic mysteries in our next segment. Having looked into the future, let's now take a step back to understand how we arrived at the concept of the Big Bang. The Big Bang theory, the prevailing cosmological model for the observable universe, didn't just appear overnight. It took decades of observation, calculation, and scientific brilliance to piece together the evidence that pointed towards this explosive beginning. In the early 20th century, astrophysicists started noticing that the light from distant galaxies was redshifted, an indication that those galaxies were moving away from us. This observation was crucial in forming the idea of an expanding universe, which led to the development of the Big Bang theory. Edwin Hubble, an American astronomer, played a pivotal role in this discovery. In the 1920s, Hubble's measurements of the distances and redshifts of far galaxies confirmed not just that the universe was expanding, but also that it was doing so at a rate now known as the Hubble constant. Then came an unexpected twist in the 1960s, when Arno Penzias and Robert Wilson stumbled upon a faint noise that permeated all of space while working on an antenna at Bell Labs. This noise turned out to be the cosmic microwave background radiation, the afterglow of the Big Bang, providing strong evidence for the theory. The Big Bang theory is a testament to the power of scientific inquiry and human curiosity. It shows how our understanding of the universe has evolved and continues to do so as we unlock more of its secrets with each passing day. Stay tuned as we delve deeper into this fascinating journey of cosmic discovery.